You've heard of Kubernetes enough. Now it's time to understand it by actually using it. And that's exactly what this series is about. So if you have heard of Docker, or if you have already gotten started with Docker, this is gonna be useful for you to understand how to build a Docker-based delivery by deploying or adding an ability to deploy your containers at scales. And what you start with is a Docker image. Now, even if you don't know about Docker, you can always go back and look at my series about Docker and understand it, or even get started with Kubernetes and have a look at it later, because I'm going to give you the images which I have already built, and you can take those images, set up a cluster on Kubernetes, Google Container Engine, and get started with Kubernetes without even understanding everything about Docker, right? Docker is useful to know, but it's not a must for this series. So if you want to understand Kubernetes and the most basic fundamental concepts, this series is for you. And this is exactly what you're going to learn in this series.
You're going to begin this section by setting up a Kubernetes cluster on Google Compute Engine, which is a managed environment, and then deploy a node application. After deploying that node application, you'll understand the concepts related to deployments, services, pods, and service discovery. You'll also learn how to scale an application either using a manual approach or using the auto scaling feature of Kubernetes, do a zero downtime deployment, and finally get a quick dive into kubectl, which is a CLI management tool for Kubernetes.
Well, Kubernetes is exciting. It's also daunting because, it's very sophisticated, and since it is sophisticated, it's created by Google and it's in Google scale, it is also a little complex to understand. There is a bit of a learning curve when it comes to Kubernetes in comparison with, let's say, learning Docker, for example, right? Now, if you want to gain expertise, if Kubernetes interests you, if you're really interested in learning Kubernetes, if you want to gain more expertise in it, I have just the right course for you. And this course caters also towards a certification that Kubernetes has, that is Certified Kubernetes Administrator. So if you're interested in learning Kubernetes further, you should definitely check out our course, which has been added in the description below and along with this video. And I'm going to include a special promo offer for you, which you don't want to miss, definitely. So check out our course, and all the best learning Kubernetes. Until next time, happy learning. Okay, add this to the summary for the UDBC. All right, now the Kubernetes deployment has really transformed this organization, because they're able to move faster with the Docker-based delivery whole pipeline, and right from the moment you check in the code till the deployment, almost everything is automated, right from the testing, the building, packaging, deploying, all of that is automated. And the best part is Kubernetes has given the much needed availability, reliability, high availability, ability to scale for the organization. So in future, they don't have to really worry about how to scale, how to deploy application, and their release process has become really shorter because now they're able to do zero downtime deployment. And this is real transformation. So the work that we have done has added a lot of value. And, again, congratulations to you for helping me transform this organization. And in the next section, you're going to start talking about how do we complete the feedback loop by using monitoring.
In this video series, I am going to explain to you the key concepts related to Kubernetes by actually taking an example of an application stack and deploying that using Kubernetes. So this is what I have. This is the application that I want to deploy. And this is an e-commerce application which has a front-end application. It is made up of all these microservices which are interconnected. And this front-end application is written in Node.js. And the catalog, the actual catalog, the images and the products are served using another service, that is catalog. This is created using a Golang, and catalog uses MySQL as a database backend. The other service that we have is the carts. This is a shopping carts service, which is a Java Spring Boot based application, which uses MongoDB as the backend. This is how the application looks like after it has been deployed. This is the front end, the scaffold that you see, and the products, the catalog, the screens that you see here, all are served out of the catalog application. And then once the carts application is deployed, you will see a shopping cart appear on this part of the screen as well. Now this is what we have to deploy using Kubernetes. Now what I already have is obviously the source code. So the source code is available. It's been written. For each of the application, there is a repository. This is for the front end, there's one for the catalog, one for the carts application, and so on and so forth. Apart from that, to deploy these applications, the first step is to write the Docker files. And the Docker files for all of these applications have been written, and using the Docker files, I already have created the images as well, which have been published here. So for each of the application that includes, let's say, front-end, catalog, carts, there is a respective Docker image. In fact, catalog has two components. One is the database, one is the application. Each of that in turn has its own image. So the prerequisite before we start deploying it on Kubernetes is the images have to be available somewhere on the registry. And this is a public registry, that is Docker Hub. Apart from that, to compile, before I start building the images, I have already created the pipelines for each of the application. This is one example pipeline for the carts application. So the carts application goes through the continuous integration on this Jenkins platform, where it goes through the tests. So I have a pipeline stages which are build, test, and package. It creates an artifact, which is a jar file, and apart from that, there's another job which creates and publishes the image to Docker in an automated way. So this is what happens whenever I make a change. It goes through the continuous integration process. If everything is okay, it publishes the image on the Docker Hub here. And this is exactly what I want to deploy at scale with Kubernetes, and that is where I'm going to need Kubernetes. Now, first of all, what is the need and the purpose of using Kubernetes? Why do we need it is what we're gonna look at in this video. Now, if I want to deploy these container images, I already have the images created, and the way I run those images is, if I have just one single machine, I could use Docker and run that as a container using docker run command. Or let's say I have a stack of application, which is front-end, cards, catalog. That's one example here. I could use Docker Compose and run it on one machine in an automated way using just one command, that is docker compose up-d. Now, in either of these situations, either using Docker or Docker Compose, I am still restricted to just one machine. It can help you to automate or run the containers on one single host. Now, the problem with that is, beyond development, for development it's okay, for local development is okay, but beyond development, you're not going to have one node to run the containers on. You'll probably have a data center environment with 50 different nodes, or definitely more than one node that you want to run the containers on. Containers also follow the immutable deployment, which means that every time there's an update, there's a change, you don't go and connect to a container and upgrade the application on it. You replace the container with a new one, which also means a new deployment every time. Now, the situation is, I have a group of servers and a group of containers to be scheduled or to be run on those. Now, my problem here is, how do I decide? The first problem that I have is, how do I decide which container runs on which host? Now, in order to make that decision, I need to first know the resource utilization on each of these machines. Imagine you are in charge of running these containers, and you have like let's say you have 100 hosts, and you want to run, let's say, 50 different containers in 1 hour. Now, when you want to launch those containers, you need to know which machines have a right to run that type of container, because some of these containers might need specific resource requirements, meaning it might have a specific amount of memory, CPU, etc., or even IO requirements and so on. So based on the resources needed, based on the availability, you will have to start making that decision. Imagine making that decision probably 50 different times a day. That can get really, really daunting, because you'll have to keep monitoring these nodes, and you'll have to make that decision manually, which will also take time, which can be dependent on a human. So if you are sleeping, nobody's there to run those containers and so on, right? So that's not a good position to be in, and this is not a manual work anyways, because you can program application which does that decision on your own. And that's the first thing that that Kubernetes does. That's the primary thing that Kubernetes is useful for. And not only Kubernetes, any container orchestration engine does that. So it takes a bunch of servers, converts it into one logical entity, one cluster, and on that cluster you start running your application. So suddenly your job becomes easier, because now you're not talking to 100 machines, you're talking to just one single entity, and you submit the jobs to that entity. That entity, in this case it's Kubernetes, is resource aware. It knows the resource availability on each of the nodes. It can make the intelligent decisions. It is programmed to select the right node for the container that you provide, based on the resource requirements and based on availability. So the first thing that a container orchestration engine does is the clustering of the nodes. And the second thing that it does is scheduling. Those are two most important aspects of a COE, or a container orchestration engine. Now, apart from this, Kubernetes is capable of scaling your applications and nodes, and load balancing. It provides fault tolerant out of the box. It gives you a way to create your application deployment, etc. And for all of these reasons, you are going to need a container orchestration engine. So to simply put, anything beyond development that you want to run your applications and containers on, you are going to need a container orchestration engine such as Kubernetes. And that is the primary role of Kubernetes, and that's the most key part here to understand about why you need Kubernetes. In this video, I'm going to explain to you why do you need Kubernetes or a container orchestration engine. Kubernetes is just an example of a type of container orchestration engine. So why do you need it? How does it work at a very high level? Let's begin with Docker. Now, Docker offers you two features. One is a runtime to run your application in this contained or a isolated environment. It provides you with isolation, so you can run two different processes in their isolated environment. One process does not affect the another, and so on, right? The second thing that Docker offers is the hermetic images, or the standard packaging format. So once you package your application along with the runtime and create an image with it, it can run on your local machine or a laptop. It can run in a dev environment locally. It can run on a cloud, in a production environment, with the same way. So that's the standardization that it offers. Now, when you create an image, how do you run it is using typically a Docker run command. With Docker, you would use those Docker run command, and you can run one container at a time on that machine. That's what you can do with Docker. Now, you can also compose it, use a Docker compose tool, and run these services together, and they are launched as interconnected stack of services, and that's what Docker Compose allows you to do. The problem with this, though, is it is limited to that one machine. You cannot cross the boundary of that host with Docker Compose. You cannot run containers on two different hosts with Docker Compose and so on. That is where the problem is when you move from dev to the higher environments like staging or a production environment, because in a production like environment, you're not going to have just one host where you're going to launch container, in which case Docker would have been enough. In a typical production environment, you'll have a bunch of servers, let's call them as nodes, and then you would have to also deploy hundreds of containers a day, because we typically do immutable deployments with containers. Now I want you to pause this video, think about the challenges that you could face in such environment when you want to run hundreds of containers on, let's say, hundreds of nodes. Note it down and then come back and resume. Now, the first challenge I am going to think about is how do I decide which container runs where, because I might have to run different types of containers on specific types of node. Let's say CPU intensive node, memory intensive node. I'll also have to know about resource availability. This is a typical scheduling problem. So the first challenge is scheduling. The second challenge is once you decide how to schedule, let's say it's not disparate set of services that you're running. We're talking about microservices which are interconnected. They need to talk to each other. So a container from one node needs to talk to the container on other. That's a networking issue. So how do you define this networking which spans across the nodes? How do you do the scheduling are the main challenges. Apart from that, you might desire certain features such as high availability, in which case you might have to deal with replication. You may want to scale your application, so auto scaling. Once you have multiple replicas, how do you connect to those? How do you distribute your traffic is where the next problem is the load balancing, or next feature you may need in your environment is load balancing. We're talking about these additional features. And then when you have one application which needs to talk to each other, to the other application, how does it discover that? So service discovery or the naming, possibly a DNS based service discovery. So that might be another feature that you may want. Another could be the fault tolerance, or self-healing. So when your application goes down or one container goes down, it needs to be detected and replaced automatically. That's the self-healing. So having those features would definitely help you run your application with high reliability. And you also want to solve the problem of rollouts. How do you go from one version to another? And when that happens, when you want to do that, you might want to define a deployment strategy. Let's say you do it in batches, one at a time, and so on. So your application rollout. So all of these features would be desired in a production-like environment. And how do you set that up? As you might have guessed, the solution can be the container orchestration engine. And that's where Kubernetes comes in. And that's why you need Kubernetes. So after answering that why question, let's now talk about how Kubernetes actually would work. Now we are talking about container orchestration here. So we would be running those Docker hosts. If you have one host, it's quite easy. You can connect to that and run containers on it. But let's imagine you have, let's say, 8 different nodes here. All of those are Docker nodes and you want to run containers on these 8 nodes. Now, either you can start talking to each of those nodes individually and make those decisions where to run those containers on which node and so on manually, or you can collect them and then put them in one logical entity. And that entity is how Kubernetes would look like to you. Because once you set up Kubernetes environment and this cluster, we are not talking to those 8 different nodes, or it could be 80 or 800 or maybe 5,000 nodes. You will always connect to just one entity, that is this Kubernetes environment. And internally it might have these masters or multiple masters, and some of these nodes would be dedicated masters, others would be just nodes. We don't have to bother about it. As far as the clients are concerned, they are not worrying about the nodes. We are not worrying about the nodes. We are not talking to the nodes at all. We are talking to just one cluster, one big entity, and that is what Kubernetes is. And that's how it looks like. That's how it works. So it collects all your nodes and creates a pool out of those nodes. And that makes it easy for you to understand, because you can always look at it as one entity, and you can run kubectl run and let's say I want to run 4 containers or pods. We send it to the cluster, and it automatically goes and launches it on some nodes. We don't have to bother about where it is running, how it is run, and so on. All we have to care about is, hey, I have this much capacity, these many CPUs collectively, and I can run my nodes on it. And when I need more capacity, I can add some more nodes to this pool. And that's how you'll have to start looking at the Kubernetes environment. You don't look at Kubernetes as, hey, I have this 4-node cluster and so on. So I just look at it as one cluster where I can run those containers, and it has these many CPUs collectively and memory collectively, and I can leverage that, and when I need more capacity, I can just scale it by adding some nodes. So that's the pool of servers which are available for this cluster. That's the right way of looking at Kubernetes, and that's how Kubernetes works. Before learning any new technology, I find it quite interesting to know the story behind it. And the story of Kubernetes starts in 2003 at Google. In 2003, Google started migrating their workloads to containers. Imagine this. The world started talking about Linux containers and containers in general in 2013 when Docker came into being. By then, Google had an experience of running their entire production systems on containers for 10 years. Now in 2003, Google had 2 types of workloads. One were the batch jobs, second were the long running process. Typically whatever we use from Google publicly, like search and YouTube and Gmails and stuff, that is typically long running processes. And then you have behind the scenes crawling happening, and then analytics and indexing process. Those are run typically as batch jobs, typically using MapReduce and so on. Now Google were using 2 different types of machines in their data centers for running these 2 different types of jobs, which was a sort of a not optimal way of utilizing resources. And they found a solution to optimize resource utilization, increase resource utilization, and achieve lower costs by using the technology which existed in Linux for a while, that was namespaces. The initial Linux containers were nothing but just a file system namespaces enabled by a technology called as chroot. Now Google started contributing to the Linux containers, and they added the features for resource isolation, and what we see as Linux containers today, much of it is contributed by Google actually, and that led to LXC, and LXC had an offshoot which is now Docker. So when in 2003 Google started migrating their workloads to containers, they needed a system to manage these containers, and that too at the Google scale. So they designed a system and named it as Borg. Borg was their unified container management platform. And 2013, there were a lot of features added to Borg as more and more projects from Google started moving to it. Borg also had certain problems. Since it evolved in an ad hoc fashion, there were a lot of different configuration languages being used, and it was also a monolithic system, difficult to scale. So Google also created another container orchestration, mainly a scalable scheduler system called as Omega, and they incorporated it sometime between 2003 and 2013. Let's now fast forward to 2013. In 2013, Docker was just released, and it was getting really popular. It was a very cool tool for development, setting up, creating these disposable development environments, and it was much faster than the virtual machines to create, to set up. And Docker started offering the ecosystem, the set of tools to make things easy to use these Linux containers and speed up your development. Now, a lot of people started using Docker really, but they quickly realized that this is a great tool for development, but what next? If you wanted to take those images built with Docker and run it at scale, you still needed some critical orchestration pieces. Mainly, to start with, you needed a scheduler, because how do you decide which containers run on which machines? You might have hundreds of machines, and you needed a scheduler to make those decisions automatically and intelligently for you. And then there were many other features needed to run those applications at scale, in a production scale, and then do it in a reliable way. Features such as networking the containers, because if you run two different containers on two different hosts, how do you connect those? And then some of the interesting features that you would need would be scaling, auto scaling, maybe replication, service discovery, load balancing, and so on. So this problem needed to be solved, and that's when three engineers from Google in 2013 started looking into how to solve this problem. And by then, Google had an experience of running the containers at production scale using their system called as Borg, which was their internal proprietary system. So they started working on a project which would turn out to be the open source version of the Borg. So they took all the learnings from building the systems such as Borg and Omega, and they started incorporating those features into an open source container orchestration engine. When they started this project, they called it as 7 of 9. Just like how Borg came from a character in Star Trek, 7 of 9 was a friendlier version of Borg in the Star Trek. So they started this project to be the friendlier version of their internal orchestration engine. And they did a great job at building a minimalistic container orchestration engine. And when they announced it to the world in 2014, they called it as Project Kubernetes. And that's how Kubernetes was born. The first version of Kubernetes to be released was in 2015. And since then, it has been one of the most popular and one of the most contributed project on GitHub. Today, Google does not own Kubernetes. When they released it, the first version of it, they announced a formation of CNCF, which is Cloud Native Compute Foundation, which is a body of Linux Foundation now, and it's a vendor neutral organization which drives the decisions in Kubernetes. There are still a lot of contributors from Google and many other companies, but it is not owned by Google anymore. It's the CNCF project today. And CNCF is the one who also drives the decisions and the certification in the world of Kubernetes. And yes, the 7 spokes that you see in the Kubernetes logo came from the project 7 of 9. Let's understand some of the most important primitives in Kubernetes, including pods, replication controllers, deployments, and services. Now, you take your application and then you Dockerize it. So the first step towards that is an image, building an image. You already know that. You take that image and you want to run that as a container. When you do that with Docker, you can run it as a container. But when you want to deploy it with Kubernetes, you take that container and package it or put it in a vehicle, that is the pod. So the unit of deployment in Kubernetes is a pod, and that's what we are going to start talking about. So let's say we want to deploy these pods in a Kubernetes environments. So how does that work is what we would look at. So let's just consider your application being packaged in the form of a pod. Let's take maybe an example with, let's say, a front-end application or a web server that you have, and along with that you need a database in the backend. So let's just take this example where you start with the application, two-tier application with front-end and DB, and both of these would be packaged as images, and then you would start running those in the pods. That's what we are going to start assuming. Now for the front-end application, you would have to build the image because it's your own application. If it is your own application, you can build an image. But if it is a database, let's say MySQL or Postgres, you can pull the image from the registry. You don't have to build it, right? So those are also called as a off-the-shelf application. Sometimes COTS being commercial off-the-shelf applications. Some of these are open source, so we won't call it as commercial. But these are off-the-shelf applications, so you can pull the images, you can create the containers and run them in a pod. So you construct a pod and you start running them. So when you want to run your application, you may want to run it with high availability. Now, how do you achieve that is where replication controllers play a big part there. And the job of a replication controller is very simple. It has only two tasks that it has to take care of, and it does it well. The first is the replication. Replication is how you decide, hey, I want to run these many instances or replicas of my application, and that's what you define with the replication controller, and it takes care of that. It does the scaling part. A manual scaling, you can define a replica count and it will scale that. Second part is the availability. Availability is important, where replication controller has to monitor for the availability of these pods, and whenever a pod goes down, it is the job of the replication controller to bring it back. So talking to the scheduler and launching a new pod is what it does. So it will constantly, in a loop, keeps on monitoring for the availability of the replicas. Replicas are of a pod. The second thing that you may want to do after this is, hey, how do I go from this version to the next version of my application? In which case you would have built a new image and you want to deploy it. And when you deploy that, you may want to define certain strategy. In Kubernetes environment, the strategies could be rolling updates or batch updates or recreate, in which case you set up a downtime and then you bring up a new version. Now, when you have these pods deployed, the next question could be, how do I send the traffic to these pods? You need to have a way to do that, and that's where services come in. And services act like a load balancer to send, and it accepts the traffic on a certain IPN port and then sends it to the backend pods. And that is the concept of services. It's mainly how you access your application, how you distribute the traffic between all the available pods is what is defined in service. And every service has an IP and a DNS or a name associated with it. So in addition to load balancing, services in Kubernetes also offer you with service discovery, because when one of your application wants to connect to the second application, how does it do that is through this endpoint, a common endpoint it connects to, that's the service, and behind the service would be the pods, and this service is exposed with the DNS, so it can connect using that name. So naming or service discovery is also what services provide. So when you deploy your applications, you'll typically need to create deployments and services. Deployment in turn will manage the replication controller. So that's why we don't talk about replication controllers separately. So replication controllers are part of deployment, and that's how it will look like. So if you have two-tier application, you would create a deployment and a service for your front-end application as well as for the database. And those are the minimum objects that you need to create when you get started deploying your application in a Kubernetes environment. In the previous video, I talked about why container orchestration engine is needed, why Kubernetes is needed. I answered that question. Now we're going to start talking about how it works, and in order to understand that, we need to set up an environment. So the first thing that you need to do is, the reason why we need Kubernetes is we want to run containers on a group of servers, and instead of talking to each of that server independently, what we are trying to do with Kubernetes is we create a cluster out of that. So that's what Kubernetes does. So now we are not talking to the group of servers, we are talking to just one entity, that is Kubernetes. And behind it, it can be like 4 servers or 400 or 4,000. You can always keep on scaling up as you need it. In fact, Kubernetes today supports about 5,000 servers. Now, in order to understand Kubernetes practically, we need to create an environment with at least, let's say, 2 to 3 nodes, and create a cluster out of that, and then start talking to that cluster, and then move on with the next concept. So I'm going to show you how to create a cluster on Google platform in this video. Here I'm logged in to the Google console, the cloud console, that is cloud.google.com, and I already have a Google account, that is my Gmail account, and since I'm logged in with that, it already shows me my login on the top right corner. And the best part about this is it allows you to try Google Cloud for free and it gives you $300 credits for 1 year, which is enough for you to run, keep running the Kubernetes cluster for months, which is great. So what I'm going to do is sign up to Google Cloud here by accepting the terms on the right hand side, choosing my country and the tax information, and providing that information here. Trust me, this is the best way to get started with Kubernetes. This is the simplest way to create Kubernetes cluster, because Google Cloud gives you a managed environment, and you can set up the cluster in 5 minutes time. And once you're logged in, so what is also assumed is you have set up the billing services. If you have not, you have to do that and take the additional steps. Once you log in, you go to the top left corner, click on that menu, go to the Kubernetes engine. Here you will see a project as well. Project offers sort of a organization or a namespace, and this might take a few minutes for you to get activated, the Kubernetes container engine, once you click on it. So you might have to wait for a few minutes here. Come back after a few minutes, you will see that option activated. So you click on create cluster, and it's really simple to create a cluster. All you have to do is, even if you don't want to provide or choose any options, all you have to do is provide just a name for the cluster. Even if you don't do that, there are defaults. Even the configuration has defaults, including the region in which you want to set up that cluster. Google Cloud provides multiple regions, and you can pick the regions possibly closest to you, or the one which is closest to your users. And then even if you don't do that, you can just choose everything default and just go ahead and click on create cluster. It also shows you the default pool. This is the actual nodes. So Google creates a bunch of nodes. Those are the virtual machines or servers on the Google platform. On top of that, it is going to set up your Kubernetes cluster. So these are the nodes where your containers would be running. And I've kept everything default, clicked on create, and it has started launching the cluster. Again, this is going to take a few minutes. So I'm going to skip forward and come back after the cluster has been created, and then start with the rest of the configurations. So there I have it. So after a few minutes, I have my cluster running. I'll just give you a quick tour of this cluster. So if I click on the cluster name, it shows you the number of nodes, where it has been created, what are the endpoints, what are the IP addresses, what is the configuration. These are the default configurations for your cluster. It shows you the pool of nodes, which I have as 3, and collectively it shows you the number of cores available for that cluster and the amount of memory. These are the 3 servers, VMs, which are created on Google Cloud compute engine. On top of that, the Kubernetes environment has been set up. So these are the actual nodes, and you see the number of amount of CPU available, as well as amount of CPU requested or being used, consumed mainly by the Kubernetes control plane, which is Kubernetes' own services. Now, if you look at show services, so if you go to the workload and show system services, you see these have been provisioned automatically by default while this managed environment has been launched. And these are the ones which are running on the nodes right now, including let's say Fluentd for collecting the logs, Heapster is a monitoring service, there is an autoscaler, there is a DNS service, there is a metric server, and so on and so forth for monitoring and stuff like that, right? And since this is a managed service, we don't have a control over this. Google automatically sets up all of these. If you look at everything else, if you just explore the tabs, you won't find much right now. We have just created a cluster successfully. In the next video, I'm going to show you how to deploy an application on top of this cluster. Again, I'm going to do that completely through the Google console this time, which is the simplest way to get started and get an understanding of how Kubernetes works. And this is in a managed environment on Google Cloud Platform. In the previous video, I showed you how to create a cluster on GCP, which is ready now. In this video, I'm going to demonstrate how to deploy the application on top of this cluster using Kubernetes. Now, the application that I want to deploy is already available as an image, and that's what I have to start with. So this is the application stack, and I have images for each of the application. I'm going to deploy just one of these applications or one of the services out of, let's say, 4 microservices. I already have an image. the image already has been tagged. So I'm going to deploy the latest version of the front-end application. So I go to workloads, click on deploy, and all I have to provide is the container image here. In fact, if you look at the right hand side, it also tells you that you have to have an image ready in order to deploy that. So in the container image box, I add my image and the tag that is colon latest. No environments or anything else that I want to provide. Initial command is already defined in the image. If I want to override that, I can use it here. And then I change the name of the application. That's the name the deployment is going to be created with. If you want to add or labels or tag those, you can do that as well. And I'm going to keep everything else simple and just click on deploy. So it is creating pods, etc. right now. And on the right hand side, you will also see what is happening, what it creates. If you want to get an understanding of what actually happens, you can look at that image and try and figure out, understand what is happening behind the scenes. Now this is the deployment which has been created. So I have deployed my workload, and when it deploys that, it creates it with the high availability as well, because it has three instances, and that's what I see. If I scroll down in the managed pods section, I see 3 pods, which means that 3 instances of that image or my application are running in a high available manner. It also has configured the autoscaler with the default CPU configuration. So if the CPU utilization goes above 80%, it is automatically going to launch new instances. So Google Compute Engine not only creates the deployment here, but also which in turn creates the pods in a high available manner. It also gives you a way to scale automatically, and that's what I see here. So if I go back to workloads, this is where I see the number of pods being deployed here, and the type is deployment as well. And I should see the graphs being updated in a few minutes from now. So once I start using and consuming these pods and the application, I should see the the traffic being generated and CPU memory disk being updated. So if you look at the right hand side, you'll see the deployments, pods, etc. services here. Now it's time to publish or expose that application. It is important step in order to access that from outside. So it will create a load balancer. I have 3 pods, but it will create a load balancer. This is called as service. So I need to define which port I want to map this from the load balancer to the actual pods. The load balancer port is going to be the one I'm going to access from outside. So I'll just pick 80 port instead of a specific application port, so that it makes it easy for me to just use the IP address and port 80 HTTP, and it will point to the application. To find out which port the application runs on, you need to know which port has been exposed as part of the application image, which is typically provided in Docker file. So Docker file has this port number which has been exposed, that is 8079. So inside each of the container, the application is going to run on 8079, which I'm going to make available using load balancer. That is Google Cloud Engine or Google Compute Engine is going to create a load balancer on its own platform and forward that 80 port to 8079 on each of my pods or containers. I'm going to explain what pods are and how are they related to containers, but we are trying to expose this application first and see how this actually works at a top level. And now that the service is created with name frontend-service, I should be able to access it using the load balancer IP and the port that I defined in the configuration, which is port 80. So I see that external endpoint and the load balancer IP, which is same IP, and the endpoint is with the port, so I can access the application. I should be able to access that application using the endpoint or the public IP :80. So I pick the public IP, it's going to port 80 anyways, and there I see my application deployed. This is my first service, which is the front end. This is just a front end, which is a scaffold, but it has been successfully deployed in a high available manner on Kubernetes cluster created using Google Compute Platform. Now, if I go back and look at the details of the service, I see the labels, I see some type of load balancer, I see some IP addresses defined, and if this is the YAML code. So Kubernetes accepts a YAML file. Now, we didn't have to write this one because Google Compute Engine accepted our inputs through a form and converted into this YAML format. But if you're gonna create your own Kubernetes cluster and start getting diving deeper into it, you need to start understanding the YAML that you could see here or explore from here. For now, we're just gonna keep it simple, deploy everything through Google Compute Engine, and try and understand what actually happened here. And that's my service created, and I have deployed the application using two things. One is the workload, which created deployment, and the service which published my application. In the previous video, I demonstrated deploying an application, that is the front-end application, on the Kubernetes engine by Google. We already have a cluster created and then the workloads defined, along with the service which exposes this application using a load balancer to the outside world. Now, I'm going to start showing you what happens in the background, what's behind the scene, and what are the primitives that Kubernetes creates and what does each of that mean, starting with deployments. So when we created the workload, it actually created in a deployment for it. And if you look at the deployment configuration, it shows you how many number of pods you have running for it. Earlier, when I created it, it showed me 3 pods running right here. Now it has scaled down to just 1. And this is dynamic scaling. And when you create it with Google Compute Engine and deploy it using this console right here, it by default creates something called as autoscaler. It's also called as horizontal pod autoscaler in Kubernetes terminology. The main purpose of that is to maintain the number of replicas and dynamically scale based on the threshold. The target here we have defined, the threshold is the metric is CPU utilization, and since there is no CPU utilization on this cluster right now, it has scaled down from 3 to 1 instances of that application. Now, whether it scales up, scales down, it does the deployment and maintains the number of replicas through something called as a concept of deployments. And the purpose of deployments is basically you want to run an application. With Kubernetes, you run it in the form of containers. And those are run through pods. We're going to talk about pods shortly. But basically, if you want to deploy an application with Kubernetes, you create a deployment. And deployment in turn creates a replication controller. It has 2 purposes. One is to maintain the number of replicas. Right now it is 1, but earlier it had 3 instances of my deployment. In fact, I can scale that manually as well and change the number of instances from this YAML configuration as well, right? So, that is something I'm going to show you in another video, the scaling part of this deployment. So 2 purposes mainly. To maintain the number of replicas, and this is useful for fault tolerance and high availability as well, because whenever any of these instances goes down, it is automatically going to create another one, maybe on another node and so on. So one of that is, this is called as replication. So deployment maintains number of replicas and replication through something called as replica set. Replica set is a type of replication controller. The second purpose of deployment is provide you with an ability to upgrade from version 1 to version 2 or from one version to another version. And you can create a strategy. You can deploy that without a downtime. You can do that with downtime. It's up to you. So it gives you the strategy to define the upgrade policy from one version to another one. So deployment does mainly 2 things. One is replication controller, controlling the replicas, and second is it offers you with the strategy. And then along with horizontal pod autoscaler, it also gives you an ability to scale out and scale in based on the metrics which include the CPU utilization. And that's the reason if I want to demonstrate deployment in Kubernetes, this is how it looks like. So you create a deployment configuration which provides strategy and replica sets. Replica set is responsible for maintaining the replicas. Replicas of what? You deploy it using a pod, so it maintains the pod specification. If you write a deployment configuration, it is going to look like this. It contains the pod specification, replica set configuration, and then the strategy. This is an example of a YAML spec for the deployment. Now, talking about replication, it maintains that using a replication controller or replica set. And the way it works is, let's say if you do not have the replication controllers, this is what would happen. Let's say you have deployed 3 tiers or 3 services, 3 applications on Kubernetes. They're running on 3 different nodes. Now, if you do not have replication controller, if one of the application, let's say just one instance of this application running here goes down, or this node, for example, the underlying node has a problem, and if that goes down, you're gonna lose your instances. And if you lose that instance, your availability is affected here. Your application is down. That could be a problem. So in order to maintain that availability and provide you with a fault tolerance or auto healing, replication controllers constantly monitor for your instances. You define the number of instances. Let's say you define minimum as 1. It is going to keep on monitoring. If there is an underlying failure or a pod goes down, or the container goes down, or the instance goes down, it will automatically recreate it, reschedule it, possibly on other nodes. And that happens in an automated way. So it is constantly monitoring for the pods, and the way it monitors it is using labels. So when you deploy your application, you label those. And I'm going to show you an example of that. This is an application. And when you deployed that application, it created these labels. So the replication controller is monitoring for anything which has a label which says app is front end. And that's what you would see here as well. If you go and look at the pod, this is a pod configuration, pod spec. There's one pod running. You see the monitoring graph for that pod as well. And the label has been assigned as app front end. And there is a replica set or replication controller which is monitoring for these pods. And the role of that replica set, typically with deployment, is to maintain the number of replicas as per the specification provided by the deployment or by the auto scaler. And it keeps on maintaining that by using something called a selector. So a replication controller has a selector, and through that selector, it is going to monitor for the available set of pods. And this is how it is going to differentiate. So this replica set is for an application called as cards. So anything which matches that, only the cards applications or instances would be monitored by this replication controller. So it has to match. So labels have to match the selectors. And earlier, Kubernetes started with replication controllers, but now it is replica set. To briefly tell you the difference between the two, this is sort of an advanced version of it, and it allows you to not only do A and B. So this is where it selects based on both A and B. It has to match both of these. Versus replica set can select, allow you to do set-based selector, where you can say A and B and either V or V2 or V3. So it allows you to do both ANDing and ORing, which gives you a better, finer grain control over selection criteria. And then you can define the strategy, which can be by default is rolling update. Rolling update maintains the the uptime of the application, so that when you're upgrading from version 1 to version 2, it does it in batches. So it will start a couple of new instances, bring down the previous ones, and then launch the new ones in a rolling manner, so that at any given point of time, even during the deployment, you have at least few instances available, either with this version or this version. You can also use another replication strategy called as recreate, whereas you bring down all the instances in a typical release that you've been cutting, and then cut over to the next version. So that's what deployments do. Deployments give you a way to run your application, run your workloads in the form of containers, and it maintains uptime, high availability, and it gives you a way to define your release strategy or deployment strategy. In the previous video, I explained to you about deployments. Now, deployments offer high availability as well as it gives you a way to define the strategy to upgrade from one version to another. Second important aspect is publishing the application using services. So when we created this workload, it started running the application, but in order for me to access that application, I created a load balancer. I had to create a load balancer, and that load balances across the number of instances available in this fashion. So you create a service gives you a way to create a load balancer, and then it balances across the number of available pods. And this is the service that I had created with type as load balancer. There are many types of services that you could possibly create, and if I look at the service configuration or details, it uses the labels and selectors to select the pods to send the traffic to. Service has its internal IP, that is internal to the cluster. It also has an external IP. This is what I'm using outside. So the purpose of the load balancer IP or the external IP, or there are various other ways to expose a service, is to expose and make it available from outside, versus cluster IP is useful for internal purposes. And if another application wants to connect to this, it also has its own internal domain name. And then service has a configuration, ports configuration, whereas the port 80 on the service endpoint points to, let's say, port 8079 on my containers. Basically, this is how the services work. So you create a service. When you create a service, this is what happened. Let's say I had 3 instances of my application, front-end application, when I deployed it, and I didn't have a way to connect to this directly. So instead of connecting to it directly, we created a service. Service gave us a load balancer, internal endpoint and external endpoint as well. And my service listens on port 80. It has a cluster IP which is internal. It also would have a domain name which can be used for accessing the service from other applications internally using a DNS service. And DNS has already been configured as part of this cluster already. And the way I exposed it was using load balancer, but there are many options to do that. You can expose it using a route, using a domain name, and that's called as ingress controller, or you can use a node port. In fact, when I created the service, it also has created a node port. You would see that in the configuration for the service itself. Let's say if I look at the details, I see all the configurations. So there's only the load balancer that I see here, but it also has a node port defined here. Let's say 31345. This is useful if I want to go and look at any of the nodes. Let's say I have 3 nodes. I can use each of that node's external public IP address and then use the port to access it. So instead of load balancer, I can also use the node IP, and let's say 31455. This is a load balancer IP. This won't work, but I could do that for the nodes. That is one way of accessing it. So load balancers are only available in the case of cloud. We're using Google Cloud, so it is easy for us to use that. But if you are using on premises, you'll probably expose it using either a node port or later on using an ingress controller or a domain name such as this. You could also use another option to expose that using external IP. I'm not going to go into details with this course. This is to basically just get a basic idea of Kubernetes and understand it at a very high level. So to simply put, this is what our path is. So the external load balancer accepts the connection here, and then it passes on to the internal service. That service internally does the load balancing. So whenever I refresh this page, it will go to a next pod every time based on the stickiness, etc., right? And that is how you expose the application using the service right there, right? So that's the concept of service here, right? So this is the basic primitive of Kubernetes. We talked about deployment, we are talking about service now, and service is useful not only for publishing the application outside, but also if you want to connect one application with another. Let's say I have an application stack, and if I want to connect this to the catalog, when I deploy the catalog, it will also create an internal service. I'll use the internal DNS and connect this application with that using the internal service discovery. I'm going to talk about the service discovery, internal service discovery in another video. But before we do that, it's important to understand how our application got deployed and in the form of pods, what pods are, and how do they work. And that's what I'm going to talk about in the next video. We've already spoken about deployments and services. Now coming back to the deployment, when we created a deployment, the way it launched the applications is not purely in the form of containers, even though these are containered applications. It launched it as pods. Now what is the concept of pod and how they are related to containers? And that's exactly what we're going to explore in this section. So what do we do when we want to launch an application with container is you take that application, package it as a container image. And that image is what you use to distribute that to others, as well as to launch the applications out of that. And when you do that, you typically have 1:1 mapping. So when you take an application container, you typically have an image which contains one single application. So there is 1:1 mapping between applications and containers, and that is good for a lot of purposes, because if you want to, there are certain situations when you want to run more than one application together on the same host, and there is no way you can do that on different hosts, right? And in these situations, you might think that, oh, since I want to run it together, why don't I put it in one container image and run it together there? Now that is typically an anti-pattern in terms of container deployments, for the reason being it becomes difficult to manage these kind of containers with multiple applications, because Docker has been created specifically for running one application in one container. Docker also attaches to the application's standard out, and that's how it fetches the logs outside. Docker also manages this process by attaching to it, so whenever the process goes down, you can have Docker automatically restart it by providing the restart policies. Now, all of that has been designed with one application running in that one container in mind. The moment you start running more than one applications, what happens with Docker is there are additional challenges. So now Docker has to attach to either this or this. And then if it attaches to, let's say, one application, it is going to manage and monitor only one for restarts, for logs, for all of these purposes. And that becomes challenging to, in case this application has a problem, or how do you get a logs out of this application becomes a challenge. So either you'll have to ignore this, or you'll have to have another service like supervisor-d or run it or something else running inside, which monitors both application in turns. And even then, separating the logs also becomes a bit of a challenge here. So it is anti-pattern to run these applications in the same container, but still you may have to run it together. So what is the solution for that? And that's where Kubernetes comes and gives you a solution, because Kubernetes allows you to run these applications together, not in one container, but it says that, hey, you want to run it together, run it in two different containers, but at the same time, I'll allow you to schedule them and host them on the same node, and give you some other ways, some additional mechanisms to make it easier for those to connect together. And that is in the form of pods. So unit of deployment in case of Kubernetes is not a container, but a pod, and pod allows you to co-locate and run these containers together. And this is what you would do. Let's say if I have two applications, instead of running it in one container, I'm going to run it in its own container, but those containers will share certain namespaces. Now it all boils down to namespaces. So when you create a container, there are up to 5 namespaces you can create. A container can have its own file system, its own network, its own host name, its own user namespace, and the PID namespace, or that's the process isolation namespace. Now when you run it in a pod, what happens here is each of the container would have its own application, have its own root file system, its own dependencies, binaries, and it gives you a way to separate that from another application. So in the same pod, you can have 2 different applications running 2 different operating system. It of course has its own process ID namespace. It also has its own root file system. That's what we looked at, but there are certain things which are common as well. So both of these containers will share the same network namespace. It will also share the same UTS or the host namespace. So that is what makes running pods possible, because pods will have the IP address. The IP address is assigned to the pods. Host name is assigned to the pod. And inside that pod, you would run one or more containers. And they can also share the disk space as well. So when you mount a file system, mount a volume, you're going to mount it on a pod, and then you can basically make it available and mount it at different locations inside 2 different containers. Same volume can be shared even from different paths. It is all pointing to the same volume, and that makes it easy to run 2 applications which are dependent on each other, or one application typically depends on another. There's an auxiliary application, and then they can communicate over local host. They share the same disk space, they share the same host name. And when you deploy it, you are going to deploy it on the same node. So anything, when you deploy a pod, it is the unit of deployment is a pod. Pod is attached to a node. So you cannot run 2 different containers in the same pod on 2 different hosts. That is not possible. It's not even an anti-pod pattern. It's not even possible. So when you deploy it, you're going to run it on the same host, even if you have multiple containers running inside it. Most commonly, you're going to have one container running inside a pod, but it is possible to co-locate those using Kubernetes. And when you deploy it, you write specs like these. So it has a schema. So it's not just for pods, but for everything else in Kubernetes. So we have been deploying it using the console that Google offers. But if you want to use a generic Kubernetes, if you have your own installation of Kubernetes, you would start writing the YAML code, or you can create a JSON equivalent of that. And every spec, whether it is pod, a deployment, or a service, can also be broken down into 4 components. That is API version, kind is pod in this case, metadata is where you define the labels and the name for it, and spec is where you define the properties of a pod. Let's say which container it has to run, and that's what you would see on Kubernetes page here. So when I go and look at the pod is running this container right here, and I can also look at the YAML spec for it. And it is just a little more complex version of the specs that I showed you. API version, kind, metadata, which also has annotations and few other configurations. It definitely has labels, and the spec contains which container is been deployed using which image, and a few other configurations, and the status obviously right here. And you'll see the same YAML for every other object as well, not only pods but also for deployments, etc. So I just described the purpose of using a pod and what it does, and it allows you to co-locate the containers together. Now in the next video, I'm going to explain the use cases where you may want to run 2 containers in one pod. Typically it is 1:1 mapping. In our example, it's going to be all applications will run through the pods, and each of that pod will contain only one container. But there could be situations where you need more than one, and those are the cases I'm going to talk about in the next video. In the previous video, I talked about the pods. What is a pod? Why it has been created? Why not run 2 applications in one container, but rather run it in one pod as 2 different containers? We talked about why and what of pod. Now we're going to talk about when you might want to create more than one container in a pod. What are the use cases and what are the design patterns? And this is the documentation from Kubernetes official page, and I've just saved it as my Evernote notebook. And this talks about 3 rather patterns or design patterns when you want to co-locate more than one containers in a pod. Now, what is definitely an anti-pattern is, let's say you have an application that we are looking at here, and this application has multiple services. There's one for front end, then there's a catalog, which is another backend service, then there is another service for cards. Now, running these containers, which are like this one application with Golang and then another with Node, and running these applications together in one pod is definitely strictly a no-no. And why is that? Is because you may want to scale just the front end. You may want to just scale catalog or cards, and each of this is a microservice. If you start packaging it together, then you start defeating the purpose of and the advantages of using microservices. Your unit of scaling when you deploy it as different pods becomes just one application, whereas if you club it together, the unit of scale becomes front end and catalog, and then cards if you club all of these together. If I want to just scale one of this, it is not possible to do that with individual, or clubbing it together in one pod. And that is when, for most of the patterns, you're going to run one application in one container in one pod. That's what you deploy. But there are situations when you may want to run more than one containers, and that's what we are talking about here. This first design pattern is called as sidecar containers. Now, sidecar has become more generic word, and even if you look at, let's say, ambassador and adapter, most of those are also called as sidecar container. The concept of sidecar container is basically you have one main application, and let's say this is a Node.js application serving the web pages, and then there's another auxiliary application. Sidecar container is typically an auxiliary application which independently has no use, but it works in tandem and supports this application and provides some service to this application. Basically, in this case, there is a Git synchronizer which collects or updates the files. Again, we looked at the pod in the previous video where we talked about two containers in the same pod can share the same mount path. That is really advantageous here because this is responsible for updating the files, whereas one application is dedicatedly serving it. So we have just split it into two functionalities. And the second question, very important one, is when do you decide to run two containers in one pod? Is you decide, or you ask this question, can I run these two services on two different nodes? In this case, it is of no use, because then how would you manage the files? How would you share it? You want this application to run along with your main application. Whereas if you decide to use, let's say, our application stack here, you can run this on one node, this another node, and they are connected over the URLs or domains or ports or something like that, and that can easily work fine. And if you can answer that question, let's say, can I run it on two different nodes? And the answer to that is yes, run it in two different pods. Simple as that. If the answer is no, you might want to consider using one pod. Now, this is the auxiliary application and a sidecar. The second design pattern is called as ambassador containers. Now, in this case, there is a PHP application here. This is an example of it. And then the PHP application connects with the Redis shards. There are more than one shard. So there is, and each of that shard may have a separate state of database. If the application wants to connect to it, it just contacts, instead of keeping track of each of the shards and adding that configuration, it connects with the Redis proxy over the local host because they share the same network, both containers in the same pod. And this connects to the Redis proxy. Redis proxy is in turn responsible for maintaining the list of shards and keeping track of it and updating it as needed. So this simplifies the work for the main PHP application. All it has to do is connect to this Redis proxy, and Redis proxy in turn is serving as an ambassador for the Redis cluster here. That's why this is called as an ambassador container or ambassador service. The third is a adapter container. So it adapts to certain thing and sends it across to external service. In this example, the application is Redis, generates the logs, and those logs are extracted, and there are specific fields which are then taken out as per the requirement, and those are sent to the external monitoring system. Could be Splunk, ELK, or some other monitoring system right here, and that's what happens here. So this generates the files, and those files are then processed by an adapter, which converts it into the format that is needed by the monitoring system. Again, as I mentioned, both of these, ambassador and adapter, also can be called as sidecar containers. Typically, that's the generic generic name for the auxiliary applications. Now again, these are the design patterns, and you might have to look at your architecture and then decide when to run two containers in one pod. This is another example that I use as part of my course, which is one is the Nginx application, which is serving the web pages. Then there's another application called as fsync, which runs the git sync and updates the files and stores it in the shared mount here. This is the main application. This is the auxiliary application. There's another example. Now it's becoming really popular. There's a service called as Istio. Istio maintains and allows you to create a service mesh where one service is connected to another. It discovers it. It maintains load balancing, routing, and a lot of other things. And for doing all of this, it runs a proxy in every pod. So this is again an auxiliary service which maintains a contact with this service, collects the data that is needed by Istio itself, and then sends it to the Istio's control plane. And in turn, that control plane makes intelligent decisions on routing, load balancing, and a lot of other things. It gets the monitoring data as well. And for making that happen, it's like an agent running on every node. And in this case, that agent, that proxy, is collecting the data and running along with the main service. And that is why this is an auxiliary service. And this runs in the same pod. So in order for setting up Istio, one of the important steps is to basically add this container to the existing pod, or existing service that you're running. So I just give you a couple of examples of when do you run multi-container pods, and 3 design patterns: sidecar containers, ambassador, and adapter. In an earlier video, I've mentioned about the services and explained how they are useful for exposing and publishing the applications outside. However, that's just one part of the job that services are useful for. The other part of the job is to do the service discovery, and that is internal service discovery between the applications. So when you want the front end to talk to the catalog, how does it work? Or when front end wants to connect with the cards, another application, how does it work is through the service discovery. Now, why is it needed is, let's assume that, let's say this is the front end application and it needs to connect with the catalog. There are 3 instances of this front end application and 2 instances of the catalog. Now, in order for each of this instance to connect to the backend application, it needs to maintain some connection information. And the way it is done in this example, I'm going to show you that configuration file itself. So this is the front-end application, and the way it connects with the backend services right now is using a very simple configuration such as this. So when it wants to connect to catalog, it is just trying to connect to it using a host name called as catalog. Now, this is really useful, and why it is useful is, otherwise, if you do not have that, you'll have to maintain the information. First of all, you'll have to go and find out the IP address of each of the services here, each of the pods here. And then for each of your front-end application, you would have to add the configuration to point to these services. And not only that, the moment you scale the second application, you'll have to go back and update the configuration on all of these 3, restart the service possibly, and that can get really messy quickly with increasing number of instances, as well as whenever you update it, it replaces the container, so it is dynamic endpoints that you have here. So instead of this, if you had one single endpoint, that is there's one single endpoint, let's say by name catalog, and that in turn maintains the list of pods available, that would be much easier. And this is where service discovery comes into picture. Now, for service discovery, there are different organizations use different external tools as well, including Consul and etcd and Zookeeper. But in case of Kubernetes comes with the DNS servers, and it comes with internal service discovery, which is what I'm going to demonstrate in this video by connecting and by launching an application for catalog and then connecting it with the front end service which is running here. This is our application stack with front end, which we're going to connect with the catalog. The catalog application repositories are here, as well as I have built the images for both catalog and catalog DB, because even though it is one service, it has a backend application, backend database that it needs to connect with. So I need to deploy two services here, one for catalog, another for catalog DB. So I go to the workload and click on deploy from here. And when I have to choose the image, so first I'm going to deploy the catalog DB application, and the image for that has been built and published on Docker Hub already. So I pick that image, image repository, which is catalog-db :latest is my image tag. And then I have to provide few configurations for catalog that includes the environment variables, because environment variables allow you to make changes to the images, and when you launch the image, if you want to make changes and update the application configurations, environment variables allow you to do that. In this case, I need to define the MySQL password empty, it's supported, and the default database for it through environment variables. I click on environment variables, add that as a Boolean property, that is MySQL allow empty password, and then provide the database, which is socksdb. So this application has been taken from microservices application by vworks, which was related to SockShop, and that's why you see the same configurations there. And I provide the name, which is catalog-db. That name is extremely important because that is how my application is connecting to the database, using name catalog-db. And on the right hand side, you'll also see what is happening, and in the diagram. So you have nodes, you have deployments, and deployments launch the pods. If I go back to the workload, it's still in progress. So I see some red, does not have minimum availability, which means that it is still launching the pods. Sometimes you might have to go and look at your resources, and if your resources are not enough for the nodes, you might have to launch one or more nodes in order to make that available. So from the node console, you can look at that. Right now I have enough capacity available in terms of hardware resources, so I just have to wait for the workloads to be available, which are now. So the catalog DB has been deployed with let's say 3 pods. So it starts with 3 pods because it has this auto scaling configuration, and it will scale it down automatically. I don't have to do anything there. Next is the catalog application. I repeat the same process. I go back to the workload, click on deploy, add my image repository, which is my username / image repository and :latest. Provide the name for the application, that is to deploy that is catalog. Again, make sure you use the same names in order for everything to work perfectly okay. And I started deploying my application, and this is the catalog. Now I'm going to show you how my front end connects with the catalog application. It uses service discovery, internal service discovery. It uses a host name rather. So front end wants to connect to catalog. It's going to use HTTP catalog, and it's going to connect to port 80. Now, in order for this to work, I need to expose the application using service. I need to create an internal load balancer, an internal service using cluster IP mechanism. I need to do that for both catalog as well as catalog DB. Anything that needs an access to incoming access, you need to create a service for that. It could just be an internal service within cluster IP as well. Now the port catalog, the app front end connects to catalog using port 80. So that's why the port I have defined is 80. But the application catalog itself might be running on some other port. If I want to find out that port, I need to go and look at either the Docker file or the Docker image description and find out which port is supposed to be exposed. In this case, it's expose instruction says 81. So I pick that port and add it to the configuration as target port. Target port is application port. That's where the pods and the application will run on. I choose the the type of service as cluster IP because I don't want to expose it outside. I don't need to do that. And this is important. The catalog as a name of the service is extremely important, because that is how that is the host name that the front end is looking for. If you miss that part, if you reconfigure it incorrectly, the service itself will not be available, and the application won't be able to connect to that because it's looking for a specific host name. I need to repeat the process for catalog DB as well. I have this is my application deployment. I see the pods running for catalog. I have a service created for catalog as well, which shows me the internal endpoint. This doesn't have a load balancer configuration. It shows me which pods it is sending the traffic to, and that happens based on labels and selectors. Labels and selectors are extremely important. Now I go back to catalog DB and click on expose the application, where I choose the port that my database would be running on. Now if I go back and look at my Docker file for catalog DB, it points to another image, which is MySQL 5.7. Now if I can go to Docker Hub, that is hub.docker.com, search for MySQL, find out the Docker file for tag 5.7, which gives me the expose instruction, which is 3306. That is the default port a MySQL database runs on. So I can just pick that and configure it here. If the ports are same, I don't have to provide it here. That is optional. Only if the ports are different, the target port is different, I have to provide that. Again, I'm going to choose cluster IP as the service type. Catalog-DB. This name is again important in order for the catalog application to be able to connect to this backend service. And now that I have both services running and sending the traffic to the respective pods, I should be able to access this application from the web browser, where I have right now just the front end application running. I can go back and try and access it from here. So this is all internal service discovery using the host names, and I have 3 applications and 3 services running. If I go and refresh this page, it loads the catalog. Thus, there you go. So that loads the catalog. It will start showing up the catalog with the the products and their description and some images related to that as well. And that is how the internal service discovery works. So services are not only useful for exposing the application, publishing the application outside, but also for internal service discovery. And we have 3 services running with their internal discovery as well as external publication using load balancer. And for each application, that's what you do. You create a deployment, you create a service. Typically you have at least 2 components, deployment and a service, unless your application does not need to be discovered. I've shown you how to create a cluster on Google Cloud Platform for Kubernetes and deploy the applications on it. So far we have created or deployed frontend and the catalog along with the catalog database. Now I'm going to give you an assignment where you would add another application, that is this cards application. Now cards has 2 components, cards and cards DB. What I want you to do is just go ahead and deploy the cards application. So right now we have 3 services and 3 deployments. Services correspond to the number of deployments and the names as well. And this is the application which has been deployed. There's a front end and then there is a catalog. Catalog serves these pages and the images as well. The next thing that you're going to do is deploy the cards. And after you deploy the cards, how do you validate it? Is basically it should show up a cards shopping cart on the top page, top right corner rather here. You may not be able to use it unless you add the database, which is okay. But you should definitely see this button right here on the top right corner after you have deployed the cards application successfully. The images for the cards application are already available here. So you can use either these images or you can build your own images and use those. And that's available on Docker Hub. So if you can use this image, which is available on Docker Hub and with the latest tag. So the image is given, the problem statement is given, you have to go ahead and deploy that and then connect it with the front end. And to connect it with the front end, I'm just going to show you the way it connects with the catalog application is from front end. Again, there is a endpoint, so API directory and endpoints.js, and this connects with the carts application using this host name called as carts on port 80. So it's going to use port 80. Do remember that. And I'm also going to describe to you what port it the Docker has been configured to expose, which is 8080. So you'll have to map, the service has to map 80 port to the target port 8080 in order to make this work, the connection work, right? So go ahead, create a deployment for the carts application and validate it by refreshing this. And if you see the carts shopping cart right here consistently available, that means it is running perfectly fine. So that's your assignment for Kubernetes. And once you complete that, you can also look at the solution, which I'm going to publish as another video. So in this video, I'm going to demonstrate how to create the carts application, and this is the solution to the assignment given to us. So this carts application is has an image which is available here. All I have to do is go ahead and deploy it along with the service that I need to create. So I'll begin by creating a workload. So I go to the workload and click on deploy. Here I would choose the image. It's the same configuration as earlier. Choose the image. And along with the username, provide the tag as well. And there are no special configuration apart from providing the name for the application. That's it. And once I do that, I go ahead, click on deploy. So this starts creating the workloads, deploying the pods, and those pods would be available in few minutes. So initially I'll see the power pods not being available with some warnings, which is okay because I can just wait and come back and see if it comes up. If it does not, we can debug further, but this is mostly a transient because it is getting deployed, getting ready, images are being pulled, the resources are being allocated, and it takes a few minutes to basically have those running. Now I see the pod status being in pending. It says container creating. It's time to expose that application using a service. Again, frontend connects with carts using port 80, and that application runs, the actual application runs on port 8080 because that's what is defined in my Docker file as a port to expose. So I copy that port and provide it as a target port. Since the service port and target port are different, I have to provide both. The service type is cluster IP, which is internal. The service name is carts, so that is important. The name of the service is extremely important. So I define the ports, type of the service, and the name, and that's pretty much everything that I need in order to have this application up and running and be discovered by other services, because we have provided the name, and that's the host name that the front end uses to connect to the carts application. And it is running now 3 pods, which would be scaled down based on the load on the servers. And if I go back and refresh the application page, I should see the shopping cart on the top right corner, which I do. And this means that the carts application has been deployed and it is running, and it is front end is able to connect to the carts application. So now I have 3 workloads. So workloads for 3 services, mainly front end, catalog, and carts, along with the database. And I have this application running right here. And that's what I've deployed using Kubernetes. And this is running with high availability and the fault tolerance and load balancing, and it has an ability to scale up as well. And that's what we're going to look at in the next video. After deploying the applications and learning about the primitives of Kubernetes, which include services, deployments, and pods, along with replication controllers, it's now time to look at few additional features of Kubernetes. One of that is scaling. So in this video, I'm going to show you how to scale your application both manually as well as using the auto scaling feature that the Kubernetes offers and which is already been configured in our cluster. First, we'll look at manually scaling the pods or the services. So I go and look at the catalog application, which is been deployed with just one pod right now. And then there's an autoscaler configured as well. So if I want to scale it manually, all I need to do is just edit the configuration, which will open up a YAML editor. And this contains the spec for the deployment for this application, that is catalog, which says replica is equal to 1. And I'm just going to change it, update it to, let's say, 3. And as soon as I save it, it starts launching the new replicas or new pods, which I see here. So which says container creating. This is a static page, so I have to basically, it does not get updated dynamically. So I need to refresh at least once to get the updates. And it's been deployed. It takes probably just few seconds in order to scale this application. And all of these applications, all of these pods would have been added to the service for the catalog as well. And these are running on different nodes. If I look at this is note down the node ID, that last string. And if I go and look at the second pod, it is not running on the same nodes. It automatically gets distributed across the nodes, and this node is a different one. If I click on the node, it shows me what all pods are running as well as the node information right here, including the utilization of that node. I can also go to the cluster, click on the cluster name, go to the nodes, click on the node, and get the same details. And when I look at the node, it shows me not only the monitoring data for the node, also the pods running on that node, including the system related or Kubernetes control information as well. And this is where I come back and check that it has been scaled. So I have been able to manually scale my application. Now this is part of the autoscaler configuration, which has defined the minimum to be 1, maximum to be 5. So in due time, since there is no load on the servers, it would automatically scale down. In order to see the auto scaling this down, scaling this in, we'll have to wait for a few minutes, come back and check. And it's already scaled down thanks to the autoscaler. So autoscaler makes sure, does a good job maintaining the fleet and reducing the workload when there is no need. Now's the time to put the autoscaler to test. And in order to do that, we need to run some benchmark or stress test application and send some, generate a load or simulate the load in order for the autoscaling to trigger automatically. And I'm going to run a load test against this URL, and I have an application just to do that. And this is the load test application. In fact, you can use this as well. This is available on Docker Hub. School of DevOps /load test is the image name. You can use the latest tag, and there is a documentation available which tells you how to run this out of a container. So you can simulate a load on any web URL, in fact, by using in this application, using these commands, by replacing just that last part where you can define the URL you want to run this stress test against. This is a Docker installation. I'm connected to a machine where Docker is installed, and I'm going to run that or launch that load test by replacing this with the URL for my application. I'm going to keep everything as default. I'm using this image called as load test, and it actually runs an application called as siege. And then I can provide the number of concurrent users that I want to simulate and how long I want to run that load test for. So concurrent users I have here are 5. I want to run constantly, so that's the benchmark test, and the time is 10 minutes. So this will pull the image, start the load test, and if I want to monitor the result of the load test as well, I can look at the logs and see what is happening with that after this application is being launched. And then I can also go back and check my application, the number of pods, and see if it scales, once the load starts triggering in. So if I go back to the console, I see the workloads, and I still have 1 pod configured or available here. I've just started the load test, so there is no load right now. It's 0 out of 80% threshold. And if I monitor it for a few minutes, the load should start going up. And every time I have to refresh and check for the load as well as for the number of pods in order to monitor that. And I see that load triggering in, because if I check the pod, and these are the monitoring details for the pod, and I see the pod now the CPU has gone up, and it should be because of the load test that I have started running. I can always go and look at the logs for the pod as well by clicking on that log link, and this takes me to the log console. It is initializing, it is loading, and it will start showing me the log details for the application running inside that container. That is for the front end. I'm going to go back to my Kubernetes console, look at the workload again, see if it has scaled up. So if I go back to the deployment for the front-end application, I still see just one pod running, but the current utilization has gone up to 12%. It's pretty slow to take up the load, so probably I need to change the configuration for my stress test and add more load by running more concurrent users. I only have 5 users right now concurrently loading this server, and it is gracefully taking it, so there's no problem. It's just 20%. My threshold is 80%. I might also have to reduce that threshold. If I want to do that, I'll go to actions and choose auto scale. In fact, you can scale from here as well. Instead of the YAML way that I showed you earlier, you can use the scale option here, and select the number of replicas, or define the auto scaling configuration from here as well. Instead of 80, I'm going to choose that to be 25% as threshold, so that it should be easier to breach. We're just doing a demo. In real life scenario, I generally use 60% or so, and it's still not it has not crossed the threshold. It's still at 21% of utilization. So I might have to do something else. I might have to go back and rerun the load test with more concurrent users. So that's what I'm going to do. I come out of that log monitoring shell, remove the load balance, remove the container with name load test, run this again. I tried a couple of configurations here, first by changing it to 10, which didn't work, and then I changed it to 15. When I changed it to 15, I also added that /index.html here, just to make sure it is actually loading that HTML page, and then it's calling the backend services as well. And then I changed the concurrent number of users to 15, which had some effect because it crossed the threshold. And if I refresh here now, it's gonna go up. So I keep on monitoring, and I might have to come back after maybe a couple of minutes, and that should do the trick, and the load should be up high enough for the autoscaler to launch a new pod. And that's what has happened. So it has the current utilization has gone up beyond 25%. It's 36% now, and it has launched a new pod. And that's the autoscaler in action. This has started scaling out. It will take some time before it launches a new pod and keeps on monitoring, and so on and so forth, right? So that's what happened automatically. So every few minutes it will trigger a new scaling event if needed. And now I just demonstrated how auto scaling works briefly. I'm going to go back and delete my pod and see how that if it comes back up, because auto scaling is both ways. It's not just about scaling out, it is also about scaling in. So right now I have 2 pods running, and if there is no load, or if the load is below 25% threshold, it should scale in, which means it should delete one of the pod. Minimum is 1, so we have defined minimum as 1, so it will keep on running 1 pod at least, and it should delete additional pods slowly and gradually after the load goes down. I have stopped my load test by killing the container, and if I come back after a few minutes and refresh, now I should see it should have been scaled down. Let's back to 1. And that's auto scaling in action. We looked at both manual scaling as well as auto scaling in this video. In the previous video, I demonstrated the scaling of application on Kubernetes, either using doing the manual scaling or using auto scaling feature. In this video, I'm going to demonstrate another feature where you can deploy your application, upgrade it from one version to another without causing the downtime. It's also called as zero downtime deployment. Let's have a look at it. List of deployed workloads that I have on my Kubernetes cluster, and I'm going to scale and deploy the front-end application using rolling updates or zero downtime deployment. In order to do that, first thing that I'm going to do is scale this application. Right now there's only one instance running. There's no fun in deploying one instance in a rolling update at all, so I'm going to change that to 8 replicas. Those replicas actually get reduced to 5 later automatically, actually, that configuration. So when I start deploying, it would be 5 replicas that is my desired number of replicas. Let's assume it's 5. And I'm gonna go ahead and create the rolling update configuration. This is where I define how to update, what is my batch size, how much time I want to wait between each of that batch. Let's say if I have a batch size of 2, 1 maximum surge and 1 unavailable, and I define 20 seconds as that minimum ready second, it would deploy with 2 in a batch of 2, so it will keep on repeating that process after every 20 seconds. So it would have a 20 seconds delay between the batches. So it is going to deploy in 4 batches here. I also need to choose the image that I need to deploy here. Now after I made those changes, if I keep on refreshing, now the desired state has changed to 5. The image that I have for frontend has only one version. That's not very useful if I want to try out with different versions of the application. I'm going to give you another image which has been created with School of DevOps as an organization. So if you go to Docker Hub and School of DevOps /frontend, that image has so many versions, so many tags, and we're going to deploy version 3 and version 4 using rolling update configuration. Now this is self-healed, so I don't have to worry about those errors, and ultimately I would have 5 instances of that front end running. Right now it's version 703, that's the default version that I have with my image. I'm going to also set up a refresh interval. So I have a plugin which keeps on automatically refreshing the browser page at a regular interval. I have defined the interval to be 4 seconds. You can also manually refresh it or install a Chrome plugin to do that. Now I have moved this to another window, and I'm going to define the rolling update configuration. This time actually I'm going to commit that configuration. Last time I was just showing it to you. I have changed the image to School of DevOps /frontend version 3.0, so v 3.0, and it has started deploying the new version. Already I see the next new version details here, and this is without downtime. So it is refreshing every 4 seconds, and as you see, the application does not go down. It is still available. Sometimes it shows version 3, that's a new version. Sometimes it shows the older version. That is expected because it is just doing a rolling update, and all of the available replicas of the pods would be added to the load balancer and would be live. That's the expected way for rolling updates. So you can have either or the previous or the new version, but you won't have any downtime. Now if you go back and keep on refreshing, you'll see that every 20 seconds a new update is rolled out. And some of these replicas are at version 2, some of those are at version 1. So I have a configuration where I want to have a surge of 1, so it has created 6 in total, 4 in the new version, 2 in the previous older version. That's what I see here. 4 updated, 6 in total, 2 are still being available. They're not available, they're being updated, and eventually all 5 would be in the desired state, and then the additional surged replica would be deleted eventually. That surge has been created just to support the deployment and have additional instances during that, and eventually you will see that all of these instances would be running version 3. So now it is load balancing and I see only version 3 now. And if I refresh this as well, I would see the same. So front-end service, the service as well is pointing to all those replicas. 5 are running. 1 is an error because it is being deleted or removed, which is absolutely fine and expected. That's the first rollout with version 2. I'm going to deploy another version. So all I need to do here. So I see the 5 replicas. You see that 5 number that's been reset to 5. I had started with 8 earlier, but it was reset to 5 later. To deploy the new version, all I need to do is go to the rolling update configuration, keep everything as same, and just update the version. This time I'm using version 4.0. So v4.0 is my tag. And again, it starts the rolling update, and I see the new version, that is revision number 3, and it is doing in batches of 2. So 2 containers are down, 2 are being updated, 1 has been created as a surge, so 6 in total, 2 are updated, and 4 are yet to be updated here. Again, this is refreshing, so I see version 4, and then I would eventually see version 3 as well. But again, as I mentioned, there is no downtime. This is without downtime. This is with 0 downtime. This is also called as rolling update because it is rolling in batches, and our batch size is 2. So I'll have to refresh this manually in order to see this in action. So eventually it should move all the replicas to version 3. And when it does that, if I go back to the web page, I should see only version 4, and I should see the newer version that I have deployed, that is version 4 only. Again, some of these are being deleted, so that's why it's in error state, because eventually once the update is complete, the older replicas would be deleted. Now I see only version 4 here, and I'm going to stop that refresh, auto refresh, because the deployment has been complete and I have moved on to the newer version from the older version using rolling update. That is how rolling updates or 0 downtime deployments work. I've demonstrated creating a Kubernetes cluster on GCP, and we have deployed the workloads and created the services. We've also tried around our hand by scaling the application as well as updating it using rolling updates. Now all of this so far that you have seen is been done using the GCP console. Now I'm going to show you how to actually manage Kubernetes cluster using the Kubernetes' own way, that is using the CLI tool that is kubectl. Kubectl is also called as kube control, and to install that you have an option to do that using this Cloud Shell. Cloud Shell is a great option because you don't have to install anything locally with Cloud Shell. Cloud Shell gives you or sets up an interface or a shell environment on the browser itself, through the browser itself. So you don't have to install anything and it configures everything on its own. So I have just clicked on that Cloud Shell and it has set up itself. It comes with the utilities, but you still need to provide the configuration. So I choose that kubectl option and choose setup, and that would help me create a shell with the environment setup for kubectl to operate. So all I have to do here is press enter, because I already see those commands for gcloud container cluster, get credentials, and then kubectl get deployment front end. So it basically goes ahead and sets up the environment for kubectl itself to operate. Now kubectl, as it is called, kubectl, kubecontrol, kubectl. I'll call it as kubectl, but you can call it either ways. So if you want to validate the setup, you run kubectl get nodes. That should show you 3 nodes that are part of this Kubernetes cluster. And if you just run kubectl, it will show you all the help, including the options that it supports. And most commonly, if you want to get information about something, you generally use get and describe. Apart from that, you can also use commands such as cluster info to get status of this cluster. So I'm going to start with kubectl cluster-info, which shows me the status of the Kubernetes master, the load balancer, the heapster, which is a monitoring service, kubedns, and metrics server. So all of these components have been deployed as part of the Kubernetes control plane, which has been set up and managed by GCP itself, or Google Container Engine to be precise, Kubernetes engine to be precise. If you just run kubectl get, it shows you all the objects that it can get information for. And it's going to be similar to what is displayed here when you choose, let's say, services or workloads, and you're going to pick the objects. For example, deployments, either use deployments or a short form which is deploy. Services is another important thing. You can use either as services, service, or SVC as the short form. So if I run kubectl get deployments, it's gonna show me the workloads. I can also use a short form which is get deploy, and this shows me the exact similar output as you see in the top window that you would have seen using GCP console. And if I want to get more information about it, I can always use describe. So I'm describing a deployment whose name is frontend. kubectl describe deploy frontend, and this shows me the details about the deployment, how many replicas are running, what is the desired size, and what each of that replica is running with. So that configuration, again, if you drill down into the workloads and click on any of the deployments, it's the similar output that you're gonna see there. Similarly, if I want to get information about services, I could use describe or get. If you just use describe services, it's going to show you the details about each and every service. I don't want that much of details. I just want to get a list of services. I'm going to get, use kubectl get services, which shows me all the services. Services act as a load balancer, and services have endpoint. Out of these, most of those are cluster IP, internal services which have internal IP. Only one has an external IP, which is the service that I have exposed for the front-end application. I could also use kubectl get SVC, which is the short form for services. So only one service has been exposed outside using load balancer. That's the one which has external IP. I can also get a list of things by adding comma separated items. So this time I'm listing pods, services, and deployment. So I'm using kubectl get SVC comma deploy comma pods. And I see 4 pods running. I can also manage the scale and replicas, so I could scale the deployment, specific deployment, with a number of replicas. This is a manual scaling, so I use kubectl scale hyphen replicas is equal to 4 for deployment. So deploy hyphen front end, deploy slash front end rather. And that deployment has been scaled. If I refresh it here, I should see it is active scaling that gradually. And if I run get commands again, I should have it should have been deployed, and I see all 4 pods running for the front end. It'll appear here if I refresh it a couple of times. And this was a very quick dive into kubectl command line tool. Once you start managing Kubernetes deployment in a production or production-like environments, you're gonna start diving into kubectl a lot, and you extensively use it, whether to run these commands or whether to apply the YAML or JSON files that you would create. So in this series of videos, you have learned about setting up a Kubernetes cluster using GCP and deploying an application. This is the Mogambo application stack that you've learned deploying, and everything that you have done so far would have been using the GCP console, which is, again, this is a Google Kubernetes engine, which is a managed service, and everything that we've done, including the workload services, publishing those services and making this available, through a browser like this, has been done through the to the GCP console. Now, if you want to dive deeper into Kubernetes and learn about it, you can also consider our course, which is an extensive course on Kubernetes, and this is one of the top courses on the Udemy platform. Currently it has close to 12 hours of lectures, plus it is growing, so we are adding a lot many features. This is one of the most comprehensive courses available on Udemy, and if you dive deeper into the topics, you will find almost everything that you would need to get started with Kubernetes available here. There are a lot of practice activities as well, so you'll see labs where you can follow the demonstrations and do it yourself, learn by doing. It is also we have added quizzes, exercises where you can actually start learning and applying the knowledge that you learned in the lectures, and learn by doing. Actually, that's the focus we have. And as you see, it is an extensive, comprehensive course with topics including RBACs, deployments, rolling updates, network policies, and so on and so forth. So if you're interested in learning Kubernetes from grounds up, and this is one of the limited courses which actually do it from grounds up without using a cloud platform. So if you want to deploy it in your own data center, you may want to consider it as well. I'm also going to include a special coupon, special offer along with this video, which you can use to avail a discounted enrollment for this course. So if you are really interested in learning Kubernetes again, you may want to consider this. With that, I'm going to sign off by saying, I hope you have enjoyed this series, and all the best learning Kubernetes.
Well, Kubernetes is exciting. It's also daunting because, it's very sophisticated, and since it is sophisticated, it's created by Google and it's in Google scale, it is also a little complex to understand. There is a bit of a learning curve when it comes to Kubernetes in comparison with, let's say, learning Docker, for example, right? Now, if you want to gain expertise, if Kubernetes interests you, if you're really interested in learning Kubernetes, if you want to gain more expertise in it, I have just the right course for you. And this course caters also towards a certification that Kubernetes has, that is Certified Kubernetes Administrator. So if you're interested in learning Kubernetes further, you should definitely check out our course, which has been added in the description below and along with this video. And I'm going to include a special promo offer for you, which you don't want to miss, definitely. So check out our course, and all the best learning Kubernetes.